Good afternoon. My name is Tony Fantasia, and I would like to welcome you to the presentation of my final project for the ADTA Deep Learning class. While I am a full-time student in the University of North Texas School of Information Science, I'm also employed as a full-time data scientist and a data pipeline engineer with Booz Allen Hamilton on a contract with the United States Air Force in San Antonio, Texas. Today we'll be discussing convolutional neural networks and how they are used to predict images from the CIFAR-10 dataset. Convolutional neural networks, or CNNs as they're often referred, are specialized networks that process data with a grid-like topology, such as digital images. These digital images are binary representations of visual data and are the key to teaching a machine how to perceive large amounts of visual data in much the same ways as the human brain. It should come as no surprise that CNNs are modeled after the human brain due to the relative ease with which we perform these tasks naturally. These processes, regardless of how natural they come to us, are not so easily achieved mechanically. A fair amount of work is required to make it possible, but once the tools and processes are known, it becomes an achievable, repeatable, and scalable model that can be tailored to an endless number of problems and questions. The full report will be available for in-depth review upon request. Before we start down this path, I would like to address one question. What is deep learning? Artificial intelligence as a functioning system has permeated our modern society in a variety of ways, from social media platform integration to online shopping, real estate, finance, and a wide variety of other domains. There are aspects of artificial intelligence seamlessly incorporated into our daily lives, and most people are completely unaware. Despite its pervasive nature, AI had a difficult time getting off the ground, and an even more difficult time growing into the being that it was primed to become. Starting in the 1950s, Alan Turing predicted supercomputers with human intelligence and logical problem-solving capabilities similar to human beings. Since then, several innovators and scientists have worked, together and individually, over the course of decades, to develop the computerized functions necessary to make it. Newell, Shaw, and Simons developed the components for logical decision-making in 1956. Weizenbaum developed the language interpretation program ELIZA a few years later. In the 1980s, Hopfield and Rumelhart developed the first deep learning algorithms allowing computers to learn iteratively through experience, and sometime between 1990 and 2000, Cynthia Breazeal created Kismet, a system designed to identify emoticon expressions. Since these individual systems have been brought together to create the first deep learning algorithms, there were numerous obstacles that needed to be overcome. Some of the more straightforward limitations involved the limitations of CPU processing and memory for the large amounts of data needed and the computational power required to process it. One of the hurdles in the 1970s involves insufficient data storage. AI systems require vast amounts of data to use as reference and cross-reference in the logical, analytical, and inferential decision-making models inherent in human beings. At the time, data storage was woefully ineffective. The second obstacle was processing speed. Computer processors today can compute millions of calculations in a matter of minutes, depending on their complexity, but their ancestors were much slower in comparison and would need time for technology to catch up. While Moore's law states computer memory and speed doubles every year, it would apparently take until the end of the decade to see any real movement due to DARPA losing their patience, pulling their funding, and grinding research down to a veritable crawl. Other limitations revealed the depth that programmers would have to dig, namely in social and psychological areas, in order to get their answers. Deep learning algorithms came to resemble the human cerebral and visual cortex because the systems had to be designed around the complexity of human perception and logical reasoning. As the fields of computer programming, systems integration, psychology, sociology, and physiology were bound together by statistical models, deep learning became a reality. Deep learning is a facet of machine learning that does a deep dive in the data to discover features and relationships using neural networks composed of digital neurons arranged in fully connected layers that develop strength of connection or weight through the process of training data over a series of execution and backpropagation. These processes allow the model to learn what worked and where corrections can be made in an iterative fashion. Deep learning allows us to achieve complex feature recognition, either in text data or image data, without the need for extensive feature engineering common in machine learning. With deep learning, the hidden layers of connected neurons of the deep learning model will identify the features through its own processes by guiding the model rather than engineering the best features. Today, we will be implementing a deep learning model using the CIFAR-10 dataset. The dataset is commonly used in deep learning for testing models of image classification. It has 60,000 color images comprising 10 different classes. The images are 32 by 32 pixels in size and 3 color layers, and the dataset has 50,000 training images and 10,000 test images. The first step in any machine learning, deep learning, or data science project is to pre-process the data. We will be defining the names of the classes over which the dataset is distributed. There are 10 different classes of color images of size 32 by 32. Once we have set the class name, we need to normalize the image so that our model can train faster. The pixel range of a color image is 0 to 255. We will be dividing each pixel of the image by 255, so the pixel range will be between 0 and 1. For the model, we will be using convolutional neural networks. There are 3 types of layers in a convolutional neural network: the convolutional layer, the pooling layer, and the fully connected layer. Each of these layers has different parameters that can be optimized and perform a different task on the input data. Convolutional layers are the layers where filters are applied to the original image or to other feature maps in the deep CNN. This is where most of the user-specified parameters are in the network. The most important parameters are the number of kernels and the size of the kernels. The convolutional layer extracts the features of the image data. We start by analyzing the influence of the nearby pixels using a filter of specific size, normally a 3 by 3 or a 5 by 5, and move it across the image from the top left to the bottom right. For each point on the image, a value is calculated based on the filter using the convolution operation. First, the edges are detected, and then the details of the image are identified, and a feature map is generated for each filter. These features are taken through an activation function that decides whether a certain feature is present at a given location in an image. In the second stage, pooling is then applied over the feature maps for invariance to translation. Pooling is based on the concept that when we change the input by a small amount, the pooled outputs do not change. We can use min pooling, average pooling, or max pooling. Max pooling provides better performance compared to min or average pooling. Simply stated, it prevents overfitting. If the model is two-dimensional or larger, the process will repeat through each consecutive convolution process until it reaches the third stage. In the third stage, we flatten all the input and pass them to the deep neural network that outputs the class of the object as a prediction of the image. A good model has multiple convolution layers and pooling layers. This slide depicts the one-layer CNN model constructed around the CIFAR-10 dataset for the initial requirement of the project. While constructing these diagrams by hand can be tedious and time-consuming, there are websites and software available that make development quick and easy. Please refer to the link at the bottom of the diagram for more information. In this project, we are using convolutional neural networks, so we will be using a convolutional layer. The most commonly used model is the two-dimensional convolution, which means that convolution takes place on 2 axes. It extends convolution to 3 strata: red, green, and blue. The other type of convolution layer is one-dimensional, which is generally used for texts, while two-dimensional models are used for images. For this exercise, we begin with a 1D model and expand to a 2D model to test efficiency and accuracy improvements. Trivial neural networks use matrix multiplication by a matrix of parameters describing the interaction between the input and output unit, which in turn results in every output unit interacting with every input unit. Convolutional neural networks, on the other hand, have sparse interaction. This is achieved by making the kernel smaller than the input. For example, an image can have thousands or millions of pixels, but while processing it using the kernel, we can detect meaningful information that is of tens or hundreds of pixels. This means that we need to store fewer parameters that not only reduces the memory requirement of the model, but also improves the statistical efficiency of the model. This layer performs a dot product between two matrices, where one matrix is the set of learnable parameters, otherwise known as the kernel, and the other matrix is the restricted portion of the receptive field. The kernel is spatially smaller than an image, but is more in depth. This means that if the image is composed of 3 RGB channels, the kernel height and width will be spatially small, but the depth extends up to all 3 channels. During the forward pass, the kernel slides across the height and width of the image, producing the image representation of that receptive region. This produces a 2-dimensional representation of the image known as an activation map. It gives the response of the kernel at each spatial position of the image. The sliding size of the kernel is called the stride. This slide shows the architecture of the single-layer CNN model for the CIFAR-10 dataset and the parameters of the 1D convolution layer. The first parameters we'll discuss are the filters or kernels. The number of values of the filters shows the number of filters from which the CNN model and the convolutional layer will learn from. From each such filter, the convolutional layer learns something about the image, like hue, boundary, and shape features. The value of the parameters should be in the power of 2. Filters can be related to anything. For pictures of humans, one filter could be designed to identify noses. And a nose filter would tell us how strongly a nose appears in our image, how many times, and in what location. This reduces the number of weights the CNN must learn, and if the location of the object changes from image to image, it does not throw off the network. Although the filter values are applied randomly during construction, the filters will update these values as the network is trained. Additional filtering layers and feature maps can be added and become more abstract as we create a deeper CNN. In the architecture data, you can see that in convolution layer 1, we're introducing a 32 by 32 pixel image with a depth of 3 for each color layer. The output shape will have 32 output channels. The second parameter is the kernel size. The kernel is one of the 2 matrices involved in the convolution process, and it will move through the image and extract features of the part using a dot product. The kernel size is composed of a dimension, height times width, of that filter and will generally have an odd number value such as 3, 5, 7, etc. Here we have used kernel size of 5, which means the filter size is of 5 by 5. The kernel is set to 5 by 5 with a stride of 1, so the filter will pass over the image, 1 column shift at a time, until the whole image is mapped to a smaller size, removing pixels until only what is needed for processing remains. The next parameter is padding. There are 2 types of padding, sane and valid. In valid padding, there is no padding of zeros around the boundary of the image, so that when convolution takes place, there is a loss of data because some features cannot be convolved due to the gradient. With sane padding, on the other hand, there's a layer of zeros padded around the boundary of the image, so there is no loss of data. Also, the dimension of the output of the image after convolution is the same as the input of the image. As you can see on the right side of the slide, the padding for our model is set to sane, indicating that we have adequately buffered our model against loss of data due to gradients. This slide addresses the activation function in the fully connected layer. The reason behind using deep learning models is to solve complex functionalities. For getting a better output, we need to fit the model in ways too complex. So we need to use functions which can solve the nonlinear complexity of the model. This is done by using an activation layer. In deep learning models, we need a minimum of one layer with activation function that will add nonlinearity to the model. Otherwise, the model will be a simple linear regression and will not achieve the desired result due to the fact that it is unable to fit the nonlinear part. There are three different activation functions that serve distinct purposes. The sigmoid function takes large, very large real numbers and squashes them down so the value range fits between 0 to 1. Next is the tanh function, which is an abbreviation of tangent hyperbolic function, which performs the same squashing function but limits the range of values between -1 to 1. Last, but certainly not least, is the ReLU function, which is an abbreviation of rectified linear unit. It is the most famous activation of deep learning due to being easier to compute because the mathematical function is more simple than other activation functions. The table displayed on the slide is the result of the one-dimensional CIFAR-10 CNN model after successfully completing 1,500 iterations through the fully connected layer. Although the initial accuracy was 27.3%, it gradually improved through iteration, averaging 61.0% and finishing with 65.2% accuracy. In this slide, we discuss how the pooling layers are used to reduce the size of the image, along with keeping the important parameters enrolled while reducing the computational burden on the model. While performing convolution, the convolutional layers keep information about the exact position of features, resulting in the not so important features also being located perfectly. Because of this, we get a side effect that even a small change in pixels or features may lead to a big change in the output of the model. Using max pooling, we solve the problem by narrowing down the scope and only considering the most important features. The pooling layer replaces the output of the network at certain locations by deriving a summary statistic of the nearby outputs. This helps in reducing the spatial size of the representation, which in turn decreases the required amount of computation and weights. The pooling operation is processed on every slice of the representation individually. In average pooling, the average value from the pool size is taken. In max pooling, the max value from the pool size is taken. Pool size means the size of the filter of which the max value will be derived. The images I have used ahead to explain max pooling and average pooling have a pool size of 2 and strides equal to 2, which means a pool of 2 by 2 will be used, and in that 2 by 2 pool, the average and max values will become the output. The pool will traverse across the image according to the value of strides. Strides indicate how much jump the pool size will make. If the stride is 1, the 2 by 2 pool will move in right direction gradually from one column to another column. If we set the stride equal to 2, the pool size will shift 2 columns at a time. Next, we come to the classification section of the model. This section consists of the flattening layer, the dense, fully connected layer, and the output layer. The flattening layer converts the 3D vector image into a 1D vector, which is required by the dense layer. The dense layer takes the flattened output and feeds it to all of the neurons containing the weight, bias, and activation passed to each element. This layer takes all the previously extracted features and uses them to train the model. To prevent overfitting, a dropout layer is added that allows unneeded neurons to be switched off or dropped during an iteration. This prevents the neurons from being adversely affected by the weights of other neurons and allows for greater generalization of the model overall. Finally, we come to the output layer, which aligns to the number of classes in the dataset. In this case, there are 10 output neurons that represent the 10 classes of images in the CIFAR-10 dataset. In order to get the probabilities of each class and account for loss, we use the softmax activation with cross-entropy loss. The output layer also contains an adaptive learning rate method optimizer known as ADTA that uses the initial gradient of the image to adapt to the learning rate. ADTA is used in place of stochastic gradient descent used in machine learning because it can update the weights after each iteration, resulting in greater efficiency and accuracy. This slide shows the results from the one-layer MNIST handwriting analysis model. Using very similar configurations to the one-layer CIFAR-10 model, we started with 25% accuracy and ended the run of 50 test cycles over 1,500 epochs with a final accuracy of 98.8%. As you can see from the rate of change, maintained a fairly consistent increase aside from 9 instances where the iteration decreases from the previous. This slide shows the table of results from the one-layer CIFAR-10 dataset. The initial accuracy was 13.3%, considerably lower than the MNIST one-layer convolution model, and completes with an accuracy of 65%. Based on the different data types, one-dimensional grayscale letters with a 1 by 28 by 28 size for the MNIST versus 3D RGB color images, which are 3 by 32 by 32 in size for the CIFAR-10 dataset. It was not a surprise that the differences would be this significant. Additional tuning of the filters, kernel size, and padding may improve these results, as well as modifying the number of layers and epochs. The next slide shows the table of final results for the modified 2-layer CNN model required for the project. By adding an additional convolutional layer, pooling layer, and fully connected layer, we were able to improve our score by an additional 3%, despite the initial accuracy being lower in the 2D model versus the 1D model. Overall, we do show an improved performance and accuracy of the model just by adding an additional layer, which required relatively minimal effort. This effort, however small, does provide improved decision-making capability and will provide the foundation for other experiments in the near to distant future. The lower graphic on the slide shows how the model can identify the class of an image despite differences in size, shape, and orientation of the object. It has learned through the training process what the general shape of an airplane or truck is, regardless of its position or orientation, and predicts its class with reasonable accuracy. These processes, as they are modified for improved performance, accuracy, and efficiency, will ultimately improve decision-making capabilities by successfully identifying classifications of objects in the data that are relevant to the problem being addressed. Models are only as good as their intended use. Development of a 1D and 2D layer CNN for CIFAR-10 data has led to a possible direct application in my work. Part of my job with the Air Force Civil Engineering Command is to provide analytical support and product regarding installation health assessments, which is basically the condition of the facilities, structures, and utilities, and their cost of maintenance and replacement. To this end, I selected a labeled dataset containing 40,000 images of 50 different Lego bricks, viewed from 800 distinct orientations. Because of their general shape and size, they are effective surrogates for architectural structures like buildings, roads, and utility lines. This dataset came from Kaggle with a usability score of 9.4 out of 10, indicating a number of criteria of usefulness has been met. The data is considered easy to understand and includes essential data such as subtitles, tags, overview descriptions, and cover images to make discovery and utilization easier. The data is classified as having rich, machine-readable file formats and metadata. While the files lack description, they do meet the additional criteria that licenses are specified, and the files are in an acceptable format for use. The data also meets assurances that the dataset is maintained through update frequency checks and has a public kernel or tags. My goal with this data set is to develop a deep learning system that can recognize and identify the geospatial data from Air Force Civil Engineering field inspection reports that use aerial photographs and drone video footage. From these reports, I hope to catalog the number and types of structures in the images and train the model to recognize satellite images of each Air Force installation and do a full inventory and condition analysis for maintenance cost estimates. This system would expedite processes that traditionally take several months to complete and even longer to receive the aggregated reports from the numerous inspectors around the world. My thought is that the Lego bricks are designed with shape and structure similar to building and common building materials and would be a natural starting point for this endeavor. In conclusion, artificial intelligence, machine learning, and deep learning provide a vast array of statistical and analytical functions that allow us to examine a variety of data types, structured and unstructured, in order to identify relationships that would not be readily apparent with basic human observation and analysis. By learning how to bring these tools and functions together in an ordered series of processes, we now have the ability to conduct large-scale, in-depth, and predictive analysis of text, speech, image, and video data. By modifying the filters and parameters of our models, we are able to tune them to any particular configuration and dial them into a higher level of accuracy and efficiency where possible. Using validation processes like holdout validation and k-fold cross validation, we can evaluate the fit of the model on a limited data sample. If the model is deemed to be a good fit, then it can be deployed and integrated into a number of different scenarios and use cases. Thank you all for joining me for this presentation. If you have any questions, please feel free to leave them in the comments section below or email me at the address specified in the summary. Take care and have a great day.